seemed to be about 4:30. So I guess we're going to get going. Hope everybody can hear me. If you can hear me, just give me a thumbs up in your camera so I know we're
My
working.
camera. How do I get my camera going?
Richard, I see you.
Okay.
Okay. All righty. Well, thank you all for joining today. My name is David Philibert, Service Advisor with the Gustav Larson Company. Today I've put together a short program. I've titled it AC Service. And honestly, I believe the best way to describe it is like an AC refresher. If you think about it, you know, I myself, and I'm sure you have too, we've been away from air conditioning now for about 8 months. And it's just nice to have these things kind of reinforced. It's my call number, 612-656-4346 if you ever need to get a hold of me. We also have a service advisor mailbox. It's monitored by 6 different service advisors across the company footprint. Any one of them can help you. And that's the service department number is 800-827-9508, option 2. We're going to discuss today is we're going to talk about a couple of things we should look at under maintenance and just general system checks as well. We'll look at some system performance. Going to look at that superheat and subcooling figures and calculation that you know, we're pretty used to it. So again, think of it as a refresher. I'm going to look at some of the electrical components, how they operate, what their purpose and function is. And I've also got some stuff in there about compressor troubleshooting. When I was creating this program, one of the things I wanted to do was touch on all the phone calls that I get, things that I get phone calls about that seem to be, you know, point of interest out there. So hopefully we can give you some good information, get you ready for air conditioning season. At the indoor unit, and I don't consider this a comprehensive list of things that you would do on normal clean and check, but these are the things that you got to hit on, even if you're going out there on just a regular service call. Check the filter, check the blower motor and wheel. One of the things I always look for on the blower wheel is the blower wheel is caked and loaded with dust and dirt and debris. You have to believe that the underside of that coil is looking about the same. So if you got a really dirty blower motor and wheel, you may have to pull a coil and at least inspect it. Condensate drain, make sure it's clear and free flowing. If there's a pump, make sure the pump is in operation. And if there's this pump safety, make sure the pump safety is working as well. While I'm down in the basement, I always thought about the humidifier bypass, make sure it is closed if they have a bypass humidifier. And take a look at the electrical connections. And this is kind of an unusual one because, of course, you want to make sure the connection has its integrity, that it's good, it's solid, we don't have any broken or, you know, loose or damaged wires. But on some systems, you almost want to take a look to make sure it's wired correctly. I've run into a lot of systems, 3-4 years old, where they were never wired correctly from at install, and the consumer's been limping along with it. Just take a look, make sure it's wired the way it should be. Incidentally, if anybody has any questions, they can just unmute themselves up in, there's some meeting controls at the top. If you join with computer audio, if you're on the phone, it's *6 to unmute. The outdoor unit, again, check those electrical connections, make sure they're good, there's good integrity. A lot of mouse damage out there over the last few years. I don't know what that's all about, but I've seen a lot of rodents chew up a lot of air conditioners and you know, heat pumps. So something to keep an eye on. Check the electrical components, the start components, the run capacitor, the contactor. Make sure they're all in good shape, that there's no spider webs in the contactors or anything like that. Fan motors and blades, and I think this is extremely important with a heat pump. Make sure that if the unit's been running through the winter, that there was no damage from ice or snow or anything building up on that blade. Take a good look at it, make sure it's in serviceable condition. Line set insulation, we've all seen it where the line set insulation is just about totally off of that line set. It's a really good idea. Check it over. If it needs some insulation added to it, add it to it, because that's going to affect your superheat at the compressor. And of course, superheat, that's compressor's #1 enemy. If it's not correct. Wash the condenser coil. Take a good look at it. You know, Train American Standard product, that's fine fin coil. It's a little bit more difficult to clean, but by the same token, I don't think it loads up anywhere near as bad as a fin and tube coil does. Check system performance. Call for cooling. Get to the thermostat. I think what I see a lot of times is I'll ask technicians, "Have you looked at the thermostat?" And they say, "Oh no, I had the consumer turn it on for me." Well, you don't really know what it's in, what mode it's in, what the set point is. So I honestly believe this is something that a technician should look at when he's there. Make sure that indoor blower starts. Make sure the outdoor unit starts. It's a good time to try and identify the type of metering device. Anything installed in the last 12 to 15 years should have a TXV for a metering device. However, I know that restrictors starting to make a comeback. Seeing a few more and more of them. So just be sure what you're working on. If it's a system you've installed, you pretty much know what your company uses. So there's not a lot of digging. You know that it's probably TXV. And of course, check the temperature difference across the coil. See if it lines up and it's in the range that it should be. I have a chart like this that's available. And if anybody would like, contact me and I would certainly be happy to send you one. This is proper discharge temperature based on dry bulb and wet bulb. You see down the left edge, you got your dry bulb temperatures, and across the top, we got our wet bulb temperatures. Of course, you got to have a way of measuring wet bulb. A lot of us do. I do recommend having a psychrometer with you so you can be fairly accurate. What I like to point out is as that wet bulb temperature goes up, your TD across your indoor coil kind of starts going down. It's not as great because you're doing so much latent work, trying to pull that humidity out of the air, trying to get that wet bulb temperature down before we can start bringing the sensible temperature down as well. So this chart can kind of illustrate, do we have the proper amount of airflow? When I was creating another slide a little further on, I was looking and found that Emerson has an app called Check Charge, and it's actually a really slick little app. It'll do the superheat calculations for you if you're charging a piston or a restrictor. It'll do the subcooling calculations for you if you have TXV, and it will also do proper discharge air temperature. Still have to punch in your parameters, the dry bulb temperature, the wet bulb temperature, and it asks what temperature you got coming off the evaporator. And it will tell you whether or not you need to add more air or reduce the amount of air going across that. Pretty slick little app. I kind of happened onto it. It's Emerson Check Charge. As you know, Emerson, Copeland, White Rogers, it's all the same company. So it's comes with quite a bit of years of experience behind it. Airflow, your supply air temperature should be within 2 degrees of that chart. You're never going to get spot on, but it should be pretty close. 2 degrees is definitely doable. Temperature lower than the chart indicates lack of airflow. You got to get that blower moving a little bit faster. Temperature higher than the chart indicates too much airflow, too much load on the systems, or something else, like could have a TXV that's partially restricted or something like that. We're just not getting the proper amount of refrigerant into the coil. So just a couple of points to look at. Make sure it's, got enough air and it's working well. Total external static pressure on our Train American Standard equipment, and I think you can apply this across the board, should not exceed 0.7 inches of water column. All the blowers in the Train American Standard equipment are rated at 0.5 inches of water column. In other words, the blower will develop the advertised airflow. So you got a 3-ton drive, you can get 3 tons out of it if you're working against 1/2 inch of static. As that static pressure increases, the airflow is going to go down. Fan performance charts are found in Service Facts. I find them very useful. On the heating side, they even have expected temperature rise based on the amount of airflow you got. So it's a good little thing to have. Sometimes they're not with the furnace, but if you don't have access to Comfort Site or AS Dealer Net, you can't pull up the book, you can always give me a call and I will certainly find it for you. This is a chart from the new S9 X2 furnaces. So these are the S series furnaces, the short cabinet 90%ers with the CTM or the constant torque motor. And the reason I have this up here is I just kind of wanted to show you, you look over here at your 0.5 static column where the blowers are rated, and this particular furnace, 60,000 BTU, it's got a 3-ton drive. On high speed at 1/2 inch of static, we're moving 1,360 CFM. So we're actually a little bit over aired for a 3-ton. But if you look down the chart, as our static pressure increases, that airflow drops off dramatically. I mean, at 0.9, you're still making it, but that blower is working hard. We're drawing some pretty high amperage, and of course, it's not the most efficient thing for the consumer. So got to keep an eye on that static pressure. Keep it down around that 0.7. 0.5 is the rated, but if you can do 0.7, you're pretty good. Where do we measure static pressure? We would measure it between the filter and the blower for a return static, which that would be a negative number. And then we measure it after the heat exchanger, but before the coil. And that, of course, would be a positive number where we're blowing. Those two numbers added together, forget the plus and minus, they really don't factor into this, is what your total external static pressure is. And that's what the blower's working against. That's where the blower performance charts are set up. That's where you kind of have a good ballpark of what you're moving, how much you should be moving. We got some other numbers on there. For instance, the static pressure drop across the coil is about 0.2. That's honestly, I think that's for the older equipment, about 10, 12 years old. On the high efficiency stuff, I'm seeing coil statics closer to about 0.26, 0.28. That's our drop across the coil. The reason for that is they're trying to make these coils more efficient, and they've really kind of tightened up the spacing on them. They kind of tightened up that fin spacing. It's a little harder to get airflow through them, and you're seeing a little bit more pressure drop across there. Down in the lower right-hand corner, you'll notice something that I kind of take to heart. Supply side static would be about a 0.35, return side static about 0.15.
Okay.
Somebody have a question? 70% of the static pressure is going to be generated on the supply side. So if those two numbers were reversed, if you had a return side static of 0.35 and a supply of 0.15, there's definitely an issue in that return. So higher static pressure number on the supply side, lower on the return, which only makes sense. When we're supplying that air, we're pushing that air, it's going to have a lot more pressure against it than as it comes down that return duct. Something that I find kind of interesting on this too is filter should have about a 0.07 inch drop for a disposable filter. We all know that everybody loves using those pleated filters. If you measure the drop across some of those things, it gets to be close to 0.3 inches. So with a pleated filter in there, takes up most of the static pressure that's in the I tell people that, the duct systems are honestly designed around those leaf catcher filters. They work great, change them once a month, but be cautious if you start seeing the heavy pleated filters, because they're really restricted to airflow. So a little bit about refrigeration. Not going to spend a lot of time on superheat and subcool. We've all done the calculations. We're all comfortable with them, I'm sure. Remember, the gauges show the saturated condition of the system. So if your suction gauge is reading 123 pounds and you got R410A in there, your indoor coil, if you lay your temperature probe on it, it's going to be running about 42 degrees. Thermometers measure the superheat and subcooling, the actual temperature of the lines. One of the things that I can't stress enough is checking your test equipment. Are your gauges accurate? I went round and round with a technician about 2 years ago. We couldn't figure out what the heck was going on. And I finally asked him, I said, have you checked your gauges lately? And he found that his low side gauge was about 25 pounds off. So all the numbers we were running over that day were totally skewed. That's why nothing made sense. So hook your gauges up to a stable tank, tank of refrigerant at a stable temperature. Use the pressure temperature chart to make sure your gauges are accurate. A lot of guys are using the electronic gauges now. Works the same way with those. Should still check them for accuracy, because I do believe they have a tendency to maybe get a little out of calibration. As far as a thermometer for checking TD across a coil or something, I strongly recommend the use of a fast-acting thermocouple type probe. We all carried the little stick in the canvas thermometers. Those things are very, very slow to react. Take a lot of time. I mean, you can sit there for 10 or 15 minutes, and those things are still settling in. As technicians, we don't really have that kind of time. A thermocouple, even the type K plugs into the meter, they're very accurate. I like those quite a bit. Digital psychrometer, to measure for wet bulb and humidity measurements, you can use a digital psychrometer in the summer and the winter. You go into houses in the winter, people are saying, I don't think my humidifier is working. You can go ahead and measure and say, well, no, it's working fine. It's accurate. You got your 35% relative humidity or what have you. Fieldpiece makes a very nice little pocket psychrometer. It's not that expensive, and I've used one for quite a few years, and it's very accurate. I like it quite a bit. There are also like the Cooper superheat thermometers. There's a red case and a blue case. One of them does humidity, one of them does not. So you can just get a regular superheat thermometer to keep an eye on the wet bulb temperature. So superheat is heat added to the refrigerant vapor above its saturation temperature. In other words, once it in the evaporator, the temperature you're reading on your gauge, the pressure you're reading on your gauge, that's the saturated condition. With using a thermometer on the liquid, on the suction line, pardon me, you'll be able to actually see what the superheat is. And superheat is extremely important. Superheat is controlled by the metering device, whatever type of metering device it might happen to be. And we're going to cover a couple of them in a minute. And it's very important to measure superheat regardless of your type of metering device. For many years, I've always heard that, well, you know, I got a TXV, so all I have to do is check my subcooling. Yes, that is correct. You charge by subcooling, but you check by measuring the superheat coming off of that valve. So it really, if you're charging a system or any service you're doing to a system with a TXV, you got to check your subcooling to make sure the charge is accurate, and then check your superheat to make sure the valve is performing well. Superheated refrigerant exists in two spaces on the system, but we're really only worried about one of them. The outlet of the evaporator to the inlet of the compressor through the suction line is superheated vapor. Superheat at the compressor should never exceed 20 degrees. Should have about a return gas temperature of less than 65 degrees. So if you got 70-degree superheated gas entering that compressor, it's not going to have enough cooling ability, and you're going to overheat that compressor. And it's really the hardest thing that compressor can do. Discharge line of the compressor would also have superheated vapor. Discharge temperature off compressor shouldn't really exceed 180 degrees. If I saw temperatures in 180 degrees or higher, I kind of start getting a little nervous and checking things over, making sure everything else is correct. Thermal expansion valves. You see them called either a TXV or a TEV. It's the same exact valve, just different connotations. They sense the suction line temperature at the evaporator outlet, and the valve will open and close to regulate the refrigerant flow to maintain superheat. Charged by subcooling, and you check with superheat. So you do have to check both readings. Restricting orifices, as I say, they are making a comeback. I'm seeing more and more of them. It can either be referred to as a piston, a fixed orifice, or a restrictor, all the same thing. Charge these by superheat. Do not charge them by subcooling. They are charged by their superheat. The required superheat depends upon the load. So you use your indoor wet bulb temperature and your outdoor dry bulb temperature, and you figure out what your superheat should be. For many years, we all carried slide charts, little superheat slide charts where you could do the calculations. Today, there's an app for that. Again, that Emerson Check Charge app, really a good little tool. I was very impressed with it when I was working with it, and it calculates superheat. Also contains pressure temperature charts for you and everything. So it's really kind of like a one-stop shop for charging and checking performance of AC systems. There's also some electronic expansion valves out there. They can be referred to as an EEV or an LEV. Either one, it's the same thing. Monitors evaporator temperature and suction line temperature to maintain superheat. TXV kind of actually monitors system pressure. That's one of the closing forces on the valve. The LEVs, they're strictly monitoring temperature, and they drive open and closed based on that. They're used in some of the outdoor units, the heat pumps, and there are air handlers with them as well. The higher end air handlers, TAM 7s, 8, 9, they all have an electronic expansion valve. So to calculate superheat, measure the suction line temperature, SLT. You read your suction pressure and convert that to temperature, and that's your saturated suction temperature, or your SST. So if you take your suction line temperature, you subtract your saturated suction temperature, that's how you get your superheat. What happened here? Okay, so a quick R410A example. And like I say, I'm not going to get into this too deep because we've done this so many times over our career. Measure your suction line temperature. It's 57 degrees. And I look at my suction pressure. It's 123 PSI. Converts over to 42 degrees temperature-wise. If I do the math, 57 degrees for my suction line temperature, 42 degrees for my saturated suction temperature, come up with 15 degrees of superheat. That's kind of textbook. I think the next slide I got. Superheat has changed over the years. As the efficiency of the equipment has increased, they've tried to squeeze that superheat up a little bit higher. Right now, high efficiency equipment, I'm seeing 15 to 17 degrees of superheat is acceptable. And the older equipment, you'll run about 12 to 14 degrees of superheat. Remember that a TXV is looking at the suction line temperature at the evaporator. It's very typical that you're going to heat up that superheated vapor as it passes through the line set, gets to that outdoor unit. That's why I say you really shouldn't see anything greater than a 20-degree superheat at the compressor. If you're really, really looking for an accurate superheat, measure it as close to the indoor coil as you possibly can. Suction gas temperature, again, should not exceed 65 degrees. This is why superheat's important. If you get up in that 60, 65 degree range in suction gas, you're not going to have enough cooling gas for that compressor. Compressor's going to run hot. And it's funny is that as your suction gas temperature goes up, the gas becomes less dense. The compressor has to work harder to compress it, and you'll get an elevated discharge temperature. And in the long run, you'll be putting, a lot of premature wear on that compressor. Subcooling is heat removed from liquid refrigerant, causes its temperature to drop below its saturation temperature. So we look at our liquid gauge, maybe you see like 380 pounds. The liquid line would have its lower temperature. That's our subcooling. Pressure temperature charts do not apply. The temperature drops without a drop in pressure. Subcooled liquid exists in a very, very small spot of this system. The outlet of the condenser to the inlet of the TXV. It's the only place you'll find subcooled liquid. Subcooled liquid should never be cooler than the air temperature that's being used to cool it. In other words, if you're working on an air conditioner on a 72-degree day and you measure your liquid line temperature and you find your liquid line temperature down around 65 or 60 degrees, you got a restriction in there somewhere, because the refrigerant should never be cooler than the air that's getting pulled across that condenser to cool it off. So you find that really cold liquid line, you probably have a restriction in the condenser. Maybe it's just a plugged liquid line filter dryer or something like that, but it is definitely cause for concern, something to keep an eye out for. So you read your high side gauge pressure to figure subcooling, and you convert that to temperature. Measure your liquid line temperature and subtract the liquid line temperature from the condensing temperature. Quick little example. I got R410A with a liquid pressure of 280 pounds. Got a liquid line temperature of 87 degrees. That 280 pounds converts over to a temperature of 91 degrees. And the line temperature is 87 degrees. You only got 4 degrees of subcooling. That condenser is starved for liquid. It's not happy. She wants some more juice in it. High subcooling, this is what you see more often than not. You got a liquid line pressure of 417 pounds on the gauge. That converts over to a temperature of 120 degrees. We got 90 degrees of a liquid line temperature measured with our thermometer. You subtract the converted pressure to temperature from the line temperature. We find that we got 30 degrees of subcooling. That condenser is flooded. There's way too much refrigerant in that condenser. Either somebody's added a lot, or you could have a restriction, a bad TXV that's not open and not allowing that refrigerant to flow enough. The required subcooling is always printed on the model number, serial number tag of our Trane American Standard equipment. It's usually 10 to 12 degrees. If you've got a really long line set, especially a line set that has excessive lift, like you're lifting up to an attic, to an air handler in an attic or something like that, you may have to add a little bit of subcooling to it. What will happen is you'll actually run out of subcooling. The refrigerant will begin to flash in the line, and that'll throw the valve totally out of skew. If it sees bubbles coming back, if it sees flash gas coming back, it really doesn't know what to do. It will usually drive closed and act like a restricted TXV. If you're working on an older system, you happen to know it's got a TXV in there, and you just don't know what that subcooling should be, the best you can do is set it at 10 degrees and check system performance. 10 degrees of subcooling will probably get you there. Only if, like I say, if you've got something that's excessively long line set or a lot of lift or something like that, that 10 degrees may not work. But for the most part, in our general installations and basements and stuff, 10 degrees of subcooling would be plenty. On the electrical side, we're going to look at a couple of electrical components. Got to touch on a couple of schematics, nothing major, and look at how to test components. Contactor, one of our most common ones, low voltage coil, high voltage contacts. Check them with an ohm meter. Typical contactors that I've checked over my career, I'm seeing usually between 20, 30 ohms on that 24 volt coil. The only caveat I'll throw out there is with trained commercial equipment. Trained commercial equipment wants 10 ohm contactor with no variance. If you get outside that 10 ohms, the board goes into a self-protection mode and it won't even energize that contactor. But the residential equipment, 20 to 25 ohms is usually what I'm seeing. Best thing I can say is if you ohm out that low voltage coil, you pull the wires off and ohm it out, and you've got less than 10 ohms there, got a shorted contactor in the residential side. So keep an eye out for that. You'll run into a couple of them this year, I'm sure. Almost all of our equipment has dual run capacitors in it. It's got 3 sets of terminals on it and a metallic case. C is the common wire, so that's power into the capacitor. H is the hermetic or the compressor terminal. F is the fan terminal, of course. Some equipment out there will have separate capacitors for the compressor and the fan, so it'll just be a single run capacitor. Start capacitor, I get a lot of calls on these. Start capacitor has a black plastic case. There's a bleed resistor across the 2 terminals. And that function of that is to keep the capacitor from being out of phase with the incoming power. This way, when the capacitor gets power, it's in a neutral state and it'll respond better. It won't spark windings. They have a high microfarad rating. 122 to 145 is very common. And it's a range. It isn't just, like one single rating. It's a range. Use it with a potential relay. The potential relay removes the capacitor from the starting circuit once that compressor starts. One thing about starting components, you can't just substitute universal stuff for it. The start capacitor and the start relay are extremely model specific, so you have to make sure what you're putting in there is the same thing that was in there. It's recommended to replace the start capacitor and a potential relay together. Whichever single component you might find has failed, you really want to replace them both. The relays, the potential relays, can easily be damaged if they're held in the start winding too long. And if that's the case, the capacitor can be damaged as well. Again, the capacitors have a microfarad range, not just a set microfarad, it's a range. And not all units will have a starter kit, assist kit. It's something that you might find that you need in certain conditions. With the advent of scroll compressors, it's less and less likely to be needed, but they are available for all our kits. And there's a lot of aftermarket kits. I always carried Super Boost, the SPP5, SPP6, something like that. Always had one of those on my truck for that compressor that just wouldn't start. Potential relay disconnects the start winding from the capacitor. The capacitor from the start winding. They are position sensitive. There are contacts inside of there that if you put this thing in the wrong orientation, the contacts will either never open or never close. So gotta keep an eye on it. A lot of times there'll be an arrow on them up or something like that. So just so you're aware, they are position sensitive. In Train American Standard equipment, the tab on the unit will always point right. I'm gonna pop back to that other slide. The mounting tab right here should always point to the right when it's installed. So just so you know, this is illustration right out of the installer's guide for a start assist kit, and you can see start assembling always with the tab to the right. Potential relays are specific to each model. There is no universal. It really has to do with the ohm value of the compressor and things of that nature. So if you've got one that's not behaving correctly, you got to get the correct one. You can't use the universal. If you notice, the contacts right here normally closed, and they're in series with that start capacitor and the start winding. So if those contacts open, or I should say when those contacts open, we're no longer going to have a connection from the start capacitor to the start winding. The coil of the relay right here is in parallel with the start winding. So it will get energized at the same time as the start winding, open that relay, drop the start capacitor out of the circuit. So it's always kind of been a little bit of a mystery. You know, people call me and talk to me about them. You know, what is it doing? And I explain it, and you can see it's really a pretty straightforward system. They operate on what they call pickup and dropout voltage, and that's where you really see the specificness, how specific these relays really are, because they'll have a very narrow band that they pick up or drop out. So pickup would be open the relay, drop out is close the relay again as the compressor comes to a stop. Here in the schematic up here, you got the high voltage. You can see where the capacitor is wired in here. Here's our little start capacitor with that bleed resistor across the terminals. The relay that opens, or the contacts that open to drop that out of the circuit. Here's the coil. If you notice, the coil can be energized either right here or right here. Either way, it's going to get power. It's going to open those contacts and take that start capacitor out of the circuit. Very straightforward wiring. Plug in pretty easy. Down here in the 24 volt, what I wanted to show you here is that this system actually has a high pressure and a low pressure control. They are in series. So you got your Y1 coming in, runs through the high pressure control, runs through the low pressure control, hits the MS, which is your motor starter or your contactor. So then another schematic, basically the same thing. Here's our capacitor. Here's our compressor right here. Run, start, common windings. This is actually a two-step scroll wiring diagram. You can see right here, they've got this little compressor solenoid. That's what loads and unloads the scroll compressor. One of the things I kind of wanted to show you here is that the low pressure control in this is actually breaking the common wire. So you'd have no connection to common. It isn't in the Y circuit coming to the contactor. It's actually on its own in the common wire. So that can be a little bit hazy to troubleshoot. You might find that you have 24 volts on either side of your contactor, but no voltage across it because of that open common if your low pressure control is open. There's a little rectifier right here. This is the solenoid in the compressor for these units is a DC voltage solenoid. So they have this little diode stack or rectifier to change AC power. They change that 24 volts AC coming from the furnace into a DC power to feed that solenoid. Going to get into a little bit of compressor troubleshooting. This is one of those things that, again, I get lots of calls on, and I really thought that, you know, guys get my take on it. You probably already all know this kind of stuff, but this is David's take. First thing you got to know is your incoming field voltage correct? Is L1 and L2 good? I got my 240 volts there. We're okay. We can continue. If I don't have 240 volts and I find a tripped breaker or an open fuse, at this point we got to take a step back, take a deep breath, and start ohming stuff out. An open fuse, trip circuit breaker could easily be caused by a shorted or grounded compressor. So you want to ohm those compressor windings before replacing the fuse or resetting the circuit breaker. When I was a young technician, I went to a job early in the morning, thought this is great. I could slam in a fuse. I'll be out of here in 20 minutes, no problem. Well, it turned out that that compressor was shorted. And when I powered the compressor up, I actually blew the little fusite, the terminal block right out of the compressor. And at 7:30 in the morning, I was showered with refrigerant oil and refrigerant. And I learned that lesson. As I've been sitting in this chair talking to people, at least 6 or 8 technicians have called me and said, yeah, I replaced the fuse, and man, you should have seen that compressor when I powered it up. So if you got an open fuse, trip circuit breaker, take a minute to ohm out that compressor. Don't always have to get to the compressor terminals to ohm the windings. We all know what that's like. You got to pull the top off, you got to pull the fan off, you got to get the compressor terminal box cover off. It can be a real bear. So I myself never had an issue with ohming out those compressor windings right from the wires. Here you got your run winding. Is this red wire coming off the capacitor? Orange wire coming off the capacitor is your start winding, and the black and blue wire coming from the contactor is your common. So you can ohm it out there. If the ohm values don't work out the way you think you should, then you probably have to pull top and get in by the compressor. But if you just ohm it out, you get your ballpark ohm value correct, I'd feel comfortable energizing that compressor. So what are we looking for? We're going to ohm those windings. The start winding will always have a slightly higher ohm value than the run winding. So to ohm out the start winding, we would go from the black and blue wire to the orange wire. Ohm that winding out, that's your start winding, record that value. On the run winding, you're going to see just a slightly lesser ohm value. The ohm values are vary based on compressor model. I can get you, if you're ever interested, if you got to know for sure, I can get you exact ohm values for each compressor model, so that you can make a confident diagnosis. But the general rule of thumb, and these are just numbers that I pulled out of the hat, the math was easy. Ohm your start to common, so your start winding, you get about 2.9 ohms, let's say. Then you ohm your run to common, you get a 1.6 ohms. So right there, you've got the first rule. Start winding slightly higher than your run winding. Then you ohm from run to start. So you're ohming just the windings right through the compressor. It adds up, should add up to what the start and run winding worked out to be. So we had 2.9 ohms on our start winding, 1.6 ohms on our run winding, and we ohmed run to start and found we had 4.5 ohms. There's no continuity to ground. That compressor motor is acceptable. It should come up and run for you. Safe to energize at least. So now we want to check, do we have our line voltage applied to the compressor? Shouldn't be anything more than 5% plus or minus the unit rated voltage. Most of our units, scroll compressors, are rated at 208 to 230 volts. So the range, when we factor in that 5% plus and minus, is 197 to 241 volts. And I just heard everybody say, wait a minute, 240 volts is very common. I've never felt this apply so much on the high end. If we're running a little higher voltage, 247, 248, compressor's still going to run, shouldn't be any motor damage. The big one here is that 197 volts. If you're down below 198, 197 volts, especially when that compressor is trying to start, you're definitely going to have some issues starting. Not going to start reliable. It's probably going to take out starting components and capacitors. So that would be a concern for me. If I saw a voltage down below 198, I would definitely be concerned. Should measure the voltage at T1 and T2 while the compressor is trying to start. A static voltage reading is nice. You're sure you got the voltage there. But what happens when you load that circuit? You flip the switch on that compressor. You want that thing to turn over and run. You got to make sure that you're up in that 198 or better volts. Always measure across T1 and T2. This is something that I hear many, many times from the field each summer. Yeah, you can measure T1 to ground or T2 to ground, and oh, gee, I got 120 volts T1 to ground, 120 volts T2 to ground, so I got 240 volts. Not true. That reading can easily be deceiving, and I'll show you why. So here's a contactor. MS on our drawings is a motor starter or a contactor. If you notice, they're clearly showing us a contact between L1 and T1. Over here on L2 to T2, that's just a bar, a shunt they refer to it as. So that's a constant connection. That connection never goes away. Let's say you have a blown breaker or fuse on line 1. Line 2 is still hot. So you're going to see voltage to ground at line 2, voltage to ground at T2. The voltage is going to come out this wire, travel through our common wire, through our start winding. It's going to wind back up on T1. So you would measure 125 volts to ground on T1 as well. But you're reading the same side of the line. You're still reading line 2. And honestly, same thing will happen if your fuse on line 2 is blown and line 1, the contactor is closed, line 1 is still hot, you're going to get a back feed back to T2. So measuring voltage to ground in this case can be deceiving. You need to go across from T1 to T2. That's where you got to have your 240 volts. So here's what we know so far. Compressor doesn't have an open, grounded, or shorted winding. We checked that. We ohmed out the compressor. We were comfortable there. Voltage across T1 and T2 is between the 197 and 240 volts. The compressor should be running or drawing locked rotor amperage. Something should be happening. If you've got voltage there, you should have an amp clamp on there when it's trying to start. You should see voltage draw on that. It will only draw locked rotor amperage until the internal overload opens. And again, I'm going to go back a slide. I know, should never do that. If you notice, here's your internal overload inside the compressor. It breaks from R to common. And this little thing right here is actually a heater. It'll provide a little bit of heat on the underside of that internal overload to get it to open a little faster. And that's an amp draw thing. So a couple of safeties built into it. You might find that open. You'd find an open winding if you measured like from R to common or start to common. You wouldn't get a connection. So causes of compressor failure. Number one cause I've seen is excessive superheat. System being low on refrigerant, restriction in the liquid line, plug filter dryer, what have you, restricted or underperforming TXV, or high load, too much airflow, high return air temperature. This one here, always measure your return air temperature. Don't guesstimate it off the temperature at the thermostat. That's something else that caught me a couple of times. You want to actually measure the return air entering the unit at the filter grill or the filter. Make sure that's what you're calculating stuff on. You could have a return duct broken apart in the attic or something like that, and you're sucking hot air into it. So Measure return error at the return to the unit. Poor oil return. This is another cause of compressor failure. Improperly sized suction line. If your suction line is too big, you won't have enough velocity to bring the oil back to the compressor. One thing I always kind of mention is be careful when you're really using existing line sets, especially if it was an old R22 system and now you're putting in R410A. R22 suction lines were sized larger than R410A should be. So there may be times when you're putting in a new R410A system, that suction line is too big and you'll have poor oil return. You might start fighting compressor failures. System low on charge. If it's low on charge, again, there isn't enough suction gas coming back to the compressor to bring our oil back. So that's a good one to keep an eye on. Low evaporator temperature. If you're running that evaporator too cold, if the evaporator is starving for air, there's not enough air flowing across it, the evaporator temperature will drop and it will start logging oil in the evaporator. I'm sure we've all done it. You cut a liquid line off an evaporator, it's full of oil. That oil's just coming back on you. It makes a heck of a mess in the basement. That's an evaporator that was either run with not enough suction velocity or low evaporator temperature, allowing that oil to pool in there. Shorted, open, or grounded. Refrigeration practices are the first thing to come to mind. A contaminated system wasn't evacuated well enough. You replaced a R22 system, you put in an R410A system, but the R22 or the previous system had a compressor failure. You had contamination in the line sets, didn't clean out. So remember that, we're HVAC guys, but we're also refrigeration technicians. So keep that in mind. Cleanliness is the most important thing you can practice. Bearing wear, metal fragments. This has to do with not enough oil coming back. The bearings will dry out. Remember now, on a scroll compressor, your scroll fitting is up at the top of the compressor. The motor's down on the bottom. If you're running low on oil, as that scroll turns, we're going to start wearing pieces off of that bearing. It's going to fall down onto the windings in the motor, and it's going to short them out. So that's another one. Again, not getting enough oil back. Internal overload opens, either excessive heat or amp jaw. Either one will do it. Like any other clicks-on, they'll cycle, maybe a couple hundred times, but eventually they just get tired of doing it. And they're going to fail in the open position, and then you'll have an open winding in the compressor. If you're replacing a compressor, if you have to do a compressor replacement, liquid line filter dryer, anytime a system is opened, and I don't even think that one's up for discussion, especially on R410A. You're cutting that thing out, you're opening that system up, please put in a new filter dryer. It'll save you a lot of hassle further down the line. If you're working on a heat pump, the liquid line filter dryer must be a biflow dryer. It's got to be able to flow that liquid in two directions. Honestly, if you're replacing a compressor and the system has a TXV, you can make, or I can make, a very strong case for replacing the TXV at the same time. If you come up to a system with a failed compressor, you really don't know why that compressor failed. So if you have a TXV that's underperforming, it's driving up that superheat, put a new compressor in, really haven't addressed the TXV issue. If you don't want to replace the TXV, if you say, there's a lot of extra work, don't want to charge the consumer, blah, 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 whatever, at least take very, very accurate startup data when you fire that new compressor. Verify your superheat is correct. So, just take that extra step. I have found that if the first compressor fails in 2 years, the replacement compressor will usually fail in a year, and so on. They get faster and faster. So really have to address the problem, not the symptom. Service practices always recommend changing all compressor starting components and contactors. Again, this is one that, you know, your company is going to have to make their own decisions how they change forward with it. If by some chance you're doing a warranty replacement, I don't think it's even a concern. Just go ahead and replace them. Take every precaution you can that that system will not have any kind of repeat failures. If the compressor was shorted or grounded, definitely perform an acid test. We sell little acid test kits. You get a little oil out of the system, check it and make sure it isn't, you know, acidic. If it is, there's a product called Acid Away, Acid Scavenger. It is the only additive Train or American Standard approves being put in their system. So Acid Away is a good little thing to do. Really, truthfully, you dump it in the suction line of the compressor before you braze it in is the easiest way to introduce it to the system. Suction filters, I'm not a big believer in suction filters. You have to make sure it's in the cooling mode. If you got a heat pump, you got to make it so it cannot go into the heating mode, because that will really wreak havoc on the system. You can only run a suction filter while you're in the cooling mode. They're usually not necessary, and they should really be removed after some runtime. The problem with suction filters is they're very, very, very good cleaners. They will scrub all kinds of debris out of that system that there is. But in doing so, they get restricted. If you have a 3-degree drop across a filter, you've got a restricted filter, whether it's suction or liquid. It's a little harder to measure a temperature drop across a suction filter, but most suction filters are designed with a port on the inlet side of the filter, a gauge port you can connect your gauges to, and there's also one, of course, on the service valve of the unit, so you can see and monitor the pressure drop across that filter. If you get 3 pounds of pressure drop across that filter, it's time to get it out of there. It'll just lead to more troubles and heartaches. Just a little bit about condenser fan motors. We're just about done here, gentlemen. Of course, it's energized at the same time as the compressor. Most of them are permanent split capacitors or PSC motors. Some of the higher efficiency units will use an ECM motor, the electrically commutated motor. That's on the higher efficiency units. Basically, those units will have line voltage applied to them at all times. So you got a 240 volt or 230 volt system. That motor's always got that voltage sitting on it, waiting for a command to run. Then there's a 24 volt signal that actually starts the motor. That signal will tell the motor when to run. It's usually in parallel with the contactor. So 24 volts is sent to the contactor, pull in the contactor, get the compressor running, and it's also sent to that motor to tell it turn on. There are no replacement modules for these motors, even though it looks like there would be. If there's a motor failure, it's an entire motor assembly change out. So, and quick little wiring diagram for one of them. This is actually this is a single compressor, 2-speed. It's got the variable speed outdoor fan motor on it. And you'll notice the larger wires coming in, of course, that's our high voltage. We've got a black and a blue and a brown and a red delivering high voltage to the motor. Green and yellow is our ground. Okay. And then we got the 24 volt signal coming into the fan motor. When I pulled this drawing out, what I noticed, and I hadn't seen this before, this is something new to me. This is actually a 2-speed fan motor. If you notice, you've got a yellow and brown wire bringing our Y1 signal to the motor. So the motor would know if it's energized on yellow and brown, the motor would understand that it's in first stage cooling, and it would probably run at a slightly lower speed. Then we've got another lead here, yellow and white, coming off our Y2. This is our Y2 coming in, comes off the little rectifier, comes up to the motor here, and that energizes the motor to run in high speed. So you see something like this, you got a 2-speed motor there. This right here, this website, fieldtechhelp.com, this is a free and open website created by American Standard and Train. And I tell you what, it is a tremendous resource. They've done a very, very good job with this. They really kind of detail a lot of the newer product, how to troubleshoot certain aspects of it. They've got troubleshooting on the electronic expansion valves, on the new CTM motors that we're seeing on everything, even the serial port communicating motors, like in the S9V and the modulating furnaces. So it's a really good website. If you're ever looking for information, give it a shot. I think it's very well worth it. That's the end of my presentation, gentlemen. It was a pleasure. I think most of you have my email address. If you don't, give me a call. I'd be happy to give it to you. I'd like some feedback. Of course, this is my first time doing a Zoom meeting due to the issues out there. So the technology is a little bit to get used to, but also the presentation. I started this presentation from the ground up, had no slides. I put them together with information that I thought would help technicians. So if you got a moment, shoot me a quick email. Let me know what you think. Change it, alter it. You know, my hopes are to have something every couple of weeks, just 45 minutes to an hour. If you got a topic you'd like more information on, let me know. Be happy to build a presentation. And with that, I thank you all for joining. Have a good day, and you know how to contact me if you need to. Bye now.
David,